Alright, now we're going to go over the midterm material. So, keeping everything in mind from the last couple videos, we have some new terms. Well, we already know them, but for the sake of argument, let's say they're new. What's this cool triangle looking thing, huh? This is called the Laplacian operator. Let's see if I can spell this correctly. Laplacian operator. That's what this is. Basically, what that means, it's the sum of these partial derivatives that are being applied to something. Let's say psi of x, y, and z. A gradient operator, that's just partial derivatives. These are the second partial derivatives, so that's the difference between those two. Spherical coordinates. Everybody remember those are? Let's see if I can remember them without looking. All right. Let's see here. X can be rewritten with r sine theta. Another sign. Phi. Y is going to be r sine theta cosine. And oh, I'm running out of room. And then z equal to r. I think it's cosine theta. All right, let's see if I remember it correctly. No. Oh, what a glaring mistake. Oh no. Almost correct. Not quite. As you can see, I had the correct answer right there, and I still messed up. Alright, this is what we need to know. Fortunately, these should be given, but all this really means is that for some circle, some spherical defined function, you're going to have a couple ways to define it. If, for example, you wanted to take the probability to find where, and remember what probability was. Let's do a little flashback. Probability of finding some x from, negative infinity to positive infinity or some range is going to be 1 for x px dx equal to 1. If you remember that. So if you had some sort of psi in spherical terms, you would have to do triple integral. Let's just do d tau. And these would be x, y, z, but in spherical terms. D tau, and you would do for all of those. And this is just showing you that the theta angle takes you from up and down, and is that a psi or phi? Psi or phi? I believe that's phi. The phi angle will take you around, so like if you can imagine around the equator. Yeah, that's phi. Alright, so blast to the past, classical kinetic energy is given by the momentum squared over 2m. This is classical. Well, as you know, this is no good here because we're doing quantum, so we have to rewrite it in quantum terms. And it's actually pretty simple. I mean, if you look at it, you just rewrite this in terms of center of mass and internal. So this is the part where I get to draw an airplane and have some fun. Not that I don't already have fun. Okay. coming out to a great start with the airplane. You know what, I probably should have done the cow and flies instead. I'll draw the cow and flies later for the Born Oppenheimer. Alright, so we have a plane. Yay. Now let's say we have a passenger inside. You know, let's say we have 4 passengers. No, 3 passengers inside. If you were to describe the kinetic energy of this plane, the center mass of the plane, it's the kinetic energy associated with the center of mass of the plane is going to be going at, you know, some sort of kinetic energy. But it is separable. This is the key. It's separable. The total energy is separable from the energy of the center of mass is separable from the energy of the internal components. These people moving around, they're internal. They're inside the plane. But the plane has a center of mass. So when we're describing the total plane kinetic energy, we have center of mass, which is, I mean, on a plane that is this mass, these people in here don't add very much mass. And we'll talk about that as reduced mass. So what they have for center of mass is going to be this classical term, now in terms of quantum mechanics, be P of x, center of mass, squared over 2 total mass. And P of x, of x mass, of x center of mass. That is the component of the entire plane. The relative x positions of these guys in here is in the second term, and then you have some sort of reduced mass. Reduced mass is the mass is multiplied over the mass is totaled as you reduce mass. So for example, in this case we'd have 3 dudes, so we'd actually have like M3 plus M3. But it's the same for anything, you just keep adding more M's. Alright, cool. What do we have here? Here we have the sum of of 3 dimensionals, Hamiltonian, the x and the y and the z. You add them up to get the total Hamiltonian operator, where these components, component of x in the h will be equal to this. So you have this eigenfunction. Yay, terms. You have an eigenfunction giving you some eigenvalue. Alright, so to recap, we have a Laplacian operator, which we can apply to any number of components, really. This psi could have, you know, just for kicks, this psi could have, these could be x1, y1, z1. And then you could also have x2, y2, z2. You could really go on all day, and then you just keep adding. You just keep adding partial second derivatives. We can rewrite this wave function in terms of spherical coordinates, which are these, that look like this. You know, for example, let's say we're modeling, you know, something here. This is our electron, for example. You know, it has some, and this is our r. It has some sort of x, it has some sort of y, and it has some sort of z. And operators. Getting into operators, we have to talk about kinetic energy. This is our momentum. This is total kinetic energy comprised of center of mass and internal, meaning they're separable. What's really important out of this is not my plane, even though it's nicely drawn. The important idea behind all this is that the kinetic energy is separable. You can take these two out. This will be really important later, looking ahead to the Born-Oppenheimer approximation. We'll talk about that later. And then reduced mass. Reduced mass we'll be using pretty frequently. It's used in the internal portion.